I guess it's time to start. Can someone
Too sweet.
someone get the door?
And Portland Metro. Thank you. Oh, I'm sorry. Same shit.
You just triggered him. Leave him alone.
It's my job.
You
Sorry.
triggered me.
All right, we're recording, so.
To correct people.
So,
No, it's literally my job.
so do we gotta keep
It
talk
is.
to a minimum?
It is not.
All right. So we talked about basically what were we talking about? We talked about side channel attack, then we went to simple power analysis, which we'll do in class or sometime. I'll take a video recording or something of it. Not sure how I'm gonna do that yet, but I'll figure it out next week. Now we went over differential power analysis, and then we're gonna go over basically we're going over correlation power analysis right now. So we got the Pearson correlation coefficient, which is just a covariance of basically two different signals or two different points. You know, if you have a correlation coefficient that is high, it ranges from -1 to 1, where -1 indicates a negative slope of the correlation. It doesn't indicate no correlation, it just indicates negative slope of 1. We take the absolute value generally, and we get from basically 0 is no correlation, all the way to 1, which is pretty much a very strong correlation. Here was the equation. Should we go over this again, or are we good? We went over this on Friday. Or wait, today is Friday. Wednesday, right? We went over this Wednesday. So again, we collect D power traces, right? The D power traces, which means we sample the signal D times. Each trace that you sample has T data points, right? H sub Di is a power estimate of a particular trace D and a particular key guess I. So I represents the key guess. HI bar is the average handling weight of the key I for all D traces. TDJ is a jth position in trace D. So again, we have capital D number of traces of T length each. TDJ is a jth position in trace D. So TJ bar, TJ bar is the average of the jth position in all D traces, right? So you take the average of all of that certain point. Want to draw it out again, or do you guys got it?
Also, the smart board is all of the above.
Oh, the smart board doesn't work either.
Looking for connection.
Oh, yeah, see this. Is it a Windows problem?
No, I
think they're really some different input.
Well, there it is.
All right. Well, no one said anything, so I'm just going to move on because we did do it on Friday.
Yeah. Wednesday.
Oh, you can't do this with so I switched to PDF.
It won't let you check pages.
I don't think so, or maybe I scroll up or something. So here's the actual equation. Rij is basically, Rij represents a correlation coefficient for guess I at point J. Guess I means, okay, well, if we have we were an 8-bit system, let's say we're 8-bit, or we're 1 byte of the AES algorithm. It's a 0 to 255, right? That's a guess range that we can have. In an 8-bit system, there's 256 possible values for the guess I. Also recall that each subkey of AES is 1 byte, noting that we don't necessarily need to do it 1 byte at a time. We could also have a situation where this encryption algorithm uses 1024 possible values, right? Or 4096 values. The guess would work the same, you just have more points. So how does our correlate equation actually help us find a key? If there's a correlation, there should be a spike at H sub Di minus H bar I and TDJ minus TJ bar. So more spike equals a correlation at that particular point J in D traces, right? That means that there's a strong correlation. So if I drew that out, I hope the smart board works this time. So basically, this is I, right? 0 to 255, and this is your y-axis. Essentially, this over here, this is a range of I. You're plotting Rij for each I, and then over here, you might have some signals, and then you might get a peak at a certain I value, and this I value over here might be 0.89, and that's where you know that there is a correlation at key equals I equals, let's say, 128 or something, and then you can take a guess that the key is 128. Okay, that's what's going on. So Rij is actually, again, I said, we're going to take the absolute value of that. Okay, so I didn't have to draw it out because it's on the next slide. In the graph below, Rij, absolute value, is plotted against I. So we see over here correlation around 53. So again, the x-axis represents key values, right? Notice that it ends at 255, although I think when I plotted, I just plotted up to this point, so it calculated the x-axis on its own. So the y-axis, on the other hand, represents the correlation coefficient, that absolute value of Rij. And you see the spike or the peak at basically key 53. So key 53, that's a decimal number, whatever that is, a hexadecimal. That would be your hexadecimal number. That could probably be the key, right? So the second spike over here is at around 105 or so, at 0.16 or 17-ish, probably more like 0.165. That would be the second highest value, third highest value, fourth highest value, right? Tapadar, you had a question?
I actually had that question. Is it a spike? Is it considered a correlation when the spike is like the tall one over there?
So in this algorithm, you pick the tallest one. You pick the highest spike because that's probably going to indicate the highest correlation coefficient. That's the highest correlation coefficient you get. Doesn't necessarily mean that that's a correct value. When you're running your test, you don't always get that.
Pretty low.
What, 0.24? In a noisy signal, that's actually pretty good. If you had a perfect system, a perfect signal, you filtered everything out, you'd probably expect something like a 0.85 or something. But one of the other reasons for that low noise, high noise and low correlation coefficient, because we're expecting something along the line of like 0.8 or something, right? The problem with this is for this particular setup, and for a lot of my setups that I do, it's kind of a noisy setup, right? So you're introducing a lot of noise, which reduces your correlation coefficient. The other thing is you don't have synchronous sampling. In this example, you want to synchronize the clock edge of your target, your victim device, to your scope. And most scopes don't do that. And in this particular case, that's partially why we get the low correlation coefficient. However, that correlation coefficient is enough, right? It's enough. All you have to do is make sure that your correlation coefficient is higher than all the other ones, right? And then you probably have your answer. So in this example, what we've done is we've taken this PSOC 4200 device connected. Notice that we don't use a power off the USB because it's particularly noisy. You're going to do this in this class. Here we'll use an MSO 4054 scope. We're probably going to use a 2000 series scope unless Phone can find another one. So basically we have our host computer, USB to UART, connected to the oscilloscope. The oscilloscope is connected, monitoring the victim device. There's also probably a link over here to basically talk. This is also a USB to UART. To send data to and from the victim device, right? Send the key to be the data to be encrypted or something like that. So here's the XMega 128 device getting attacked. In this case, I'm using some other setup. Notice the filtering capacitor as well. This thing is very noise sensitive. So here is a waveform for the 128 XMega. We're using the default AVR crypto lib, 2 millivolts per division, 10K samples, 100 megasamples per second. So you can see this distinct signal, right? if you just look at what do you call it, simple power analysis, you could probably tell there's something going on over here, right? But within one of these signals or one of these areas over here, you'll probably find a key of interest, right? Remember that earlier slide where I showed you, for a value of the key value, fixed key value of 15, right? Key value is equal to 15. You XOR it with something like 23, XOR it with 47, or F3 or something like that, or you XOR it with different values, and you get a series of peaks, right? You get those series of peaks that are distinct, right? And those distinct peaks give away basically which data, what key is being processed, right? So here's a setup on my desk where I did this. We'll need an external power supply over here because of the noise issue. If you were to connect this USB device directly, then you'd be in a situation where too much noise and you'd even get a lower correlation coefficient. So for the power monitoring or EM monitoring equipment, circuitry is hooked up to the target device. We feed the target device plain text and ask it to perform an encryption. And we assume that the key is already stored in the device. The encryption key, the 128-bit encryption key. Let's see, it must be a number of encryptions with the same key but different plain text. So okay, so we run the same. We run a series of encryptions that, remember the capital D traces, right? We capture capital D traces of length T, right? So we have to capture quite a few traces, and during the encryption operation, traces recorded. If ciphertext or plaintext is available, it's also recorded. It depends, right, whether we want to attack the front end of the algorithm or the back end. So a trace will contain a large fixed number of data points, which can be limited to the region of interest by the attacker. Attacker knowledge may be used to reduce the number of data points required. So what I'm saying by that statement is this. We had all this data, right? We had all this data, but the truth of the matter is you can zoom in on one particular point. There could possibly be 1 to 10 or however many points, but there could, if you could find that single point where that XOR store operation is running for that algorithm, or that substitution step for the case of AES, if you could find the spot where that operation is taking place, and you only capture this one spot, you can actually figure out, without capturing any of this over here, right? You wouldn't have to capture any of this over here, right? I'm just drawing squiggles now. So you only have to capture one data point. If you can find that particular data point that has a substitution step, that substitution box, or that unique XOR operation, you only need one data point.
So are we using the average of the, if we're taking multiple samples, are we going to use the average and look for the place on the average? Or you use the average to find the highest
No.
and go?
No, we use multiple samples for this purpose over here. Let me erase this.
Good idea.
Wow.
Tiny eraser.
If you circle the whole area with the eraser, it doesn't erase everything inside?
It's not working.
It's because your portion of it is above the.
Well,
next to your desk and do like that.
it doesn't matter. They used to have a separate eraser, but this board only has markers now.
Do you want to see something?
Oh, like an old.
Yeah, the old style. What was I going to say? Oh, to answer your question. So we take multiple samples, right?
Yeah.
Capital D number of traces. Each trace,
Are you serious?
the data changes randomly, right? Each time the encryption occurs, the data points change randomly.
That's true.
Okay. So the data points change randomly each time you run the encryption. So by using different values each time, on average, it's going to produce that profile. Once you produce those profiles of those, let's say 256 values, once there's a correlation at that point, you can probably determine the correct key from using that Pearson correlation coefficient. That's how we're doing it. And Pearson correlation coefficient normalizes the data set. So it gives you a correct, or it gives you a value relative to the overall signal. Yeah. Okay, so note that much of the process makes it very unlikely that attacker would be able to perform the system in a real-time environment. You're probably not going to be able to get away with this at a supermarket or something like that.
Shit.
Huh?
Well,
Here, hold on, let me look all this stuff up.
Yes.
I mean, isn't supermarket a real-time environment too?
Huh?
Isn't supermarket a real-time environment?
It is a real-time environment.
So whatever that. Yeah, what does that? What does that mean? It's like what is a real-time environment?
Like
So
it's
what is
actively
it?
You're trying to attack it while it's in use, is what I was trying to say with that statement. You have to bring it back to the lab and analyze it.
Gotcha. Come on.
So the attacker would have much higher success if you perform it in a lab environment and have knowledge, previous knowledge of the code, right? If you have insider information on this, and I think I talked about insider information earlier in the class, a disgruntled employee or something who knows how the code works or who's had exposure to how your company operates and how the code's written, that could help the attacker, right? It is a significant problem, this insider threat. Like, let's say I work for OIT now, but I get disgruntled, I become a disgruntled employee, right? What happens if I want to come back in and, you have to make sure that they remove all your security privileges and stuff like that. So there's a social piece of that too. So the victim device, in case of the PSOC 4200, was loaded with a firmware to perform AES 128 encryption in electronic code book mode. Again, the ECB mode is basically just run the encryption again and again and again without any block chaining, right? Loaded with a default encryption key, tiny AES, or the default ADR cryptolib. The victim code provides an output trigger when the victim device performs the most vulnerable part of the encryption process, which is the substitution step, right? The sub-byte step, the nonlinear sub-byte step, the lookup table. That's the most vulnerable part of this algorithm. And again, remind yourself that remember the algorithm. You're attacking at the algorithm level, but you can also attack at a instruction level, but where you attack each individual instruction. But in this case, we're attacking the algorithm, a section of the algorithm.
So in this case, it's not a side channel attack.
It's still a side channel attack.
Yep.
It's still a side channel attack. I'm just attacking with the instruction. A single instruction can get attacked, right?
Yeah.
A discrete operation like a load or a store on a microcontroller can get attacked. We can figure out what it's doing. That is still a side channel attack. Right? Same setup. With the AES, it might be a string, it might be a longer period of window that you monitor the code for, and you attack that section of the code. So, for example, if I'm looking to attack, to figure out what an XOR operation is doing, I'd look at that single XOR instruction. But with the substitution step, you might be looking at the store instruction, the load instruction, right? All of these may give you more clues. So it's a collection of instructions that you might be able to attack. Right? Multiple data points leak information, but recall that the store is the noisiest. And load. It's a host computer set up to transmit 16 bytes of predefined plain text to the victim at a time, as well as a message to tell the victim to perform an encryption. Once the encryption is performed, the host computer receives the data from the oscilloscope and stores it into the array. So a lot of the stuff that we're doing in this class is automated. We're just going to automate the scope, so we really don't want to actually get all that data by hand. It would be a big pain in the butt. So process is repeated multiple times up to the capital D number of traces requested by the host computer. Number of traces collected and data points per trace depends on multiple characteristics of the system under attack. Right? if you have a particularly noisy power supply, what you can do to overcome that signal is to just oversample, sample more. If you have a signal that has clock jitter in it, what you could do to a certain point is just oversample more samples, right? Just oversampling would increase the effectiveness of the attack, although or increase the sample rate, right? So what I meant was you either increase the number of samples you capture, so increase the number of D, or increase the number of T, right? The traces and the points in the trace, or increases the number of traces itself. Those two can both help overcome like clock jitter and skew, right? The number of data points required varies, but a synchronous attack will always require fewer than asynchronous attack. So Colin O'Flynn had this idea, or introduced the idea of synchronous sampling versus asynchronous sampling. Most of the sampling we do in lab is asynchronous sampling. Asynchronous sampling is basically your oscilloscope is just going to capture stuff, whereas with its own clock signal, it generates its own clock signal. But with synchronous sampling, the oscilloscope or whatever capture device you're using synchronizes, uses the same clock signal from the device, the target device. So the target device and the oscilloscope are synchronized with the same frequency, same clock signal. With that comes the ability to have a better, basically, synchronization on the clock edge. Once you have the clock edge synchronized between the scope and the target victim device, you require less samples because you eliminate that clock skew or jitter of the two clocks. Once you eliminate that, it's cleaner. Yes, it's cleaner. And then you require less samples to basically perform your attack. Right? So that's why you would do synchronous sampling versus.
Synced up, but it seems like it'd be a pain.
I use a chip whisperer. There's something called the chip whisperer. You can look it up, and I do have a chip whisperer light here if you want to play around with it. So noisy system requires more traces. Blah, blah, blah. Also, oscilloscope was automated using TechVisa and Python. Number of required traces is too large for this process to be done by hand. We really don't want to do this by hand. Okay, so we repeat the process on, oh wait, did I go over this slide?
You just went the wrong way on process, but
There should be at the
one, there you go.
Okay, so after data is collected, code from O'Flynn's manual, CPA attack, correlation power analysis attack is used. Data similar to the table shown is generated. Of the 16 bytes of AES 128, the code generates a partial guessing entropy. So what a partial guessing entropy is basically a measure of how many values have a higher correlation coefficient than the actual correct value. You need to know the actual correct key to calculate the partial guessing entropy, right? So from 0 to 255 values, a value of 0 indicates it's a correct key. A value of 100 indicates that 100 other values were ranked higher in your sample than your actual correct key. That's what the partial guessing entropy measures. Okay. Questions so far? No?
So that one.
zero.
Hold on, we have two questions. Wilsonville?
Hey, yeah, sorry, this is Steven. So the 01 under 08 in the key there towards the end of the graph, so that actually is a lower guess, like it's
There
a
was-
less accurate guess?
So for PGE 01, it means that key 08, it means that there was one key ranked higher than the correct key. There's one.
key right now. What about with respect to that key?
What?
Oh, gotcha. So the correct key is everything on the top line there, and there's the underneath was how many times something else got in front of it and was accidentally guessed.
Right. Well, it wasn't accidentally guessed, but the ranking of the guessing, 08 over there, there's one value that is.
Embedded guess.
Sorry, 08 is an incorrect guess, I believe. So there's an actual correct value, but it was off by one, is what it's saying. There was one guess. The guess was there's one guess that ranked higher than the correct value. You kind of follow me on that?
So 08 is wrong.
Oh, that's right, because each of these keys is only 1 byte long. So these are the
Right.
guess this is the PGE table for each separate guess using a
So,
key.
right.
byte.
So this is AS 128. So there's 8. Wait, no, there's not 8. There's 16. There's 16 different bytes. So it's guessing for each byte. So for this 08 and 01, if you get a 00, it means okay, you got the correct value. But for an 01, it means that there was one guess that ranked higher, that had a higher correlation coefficient than the correct value. Yes, Tamadar?
This is for the key.
This is for the key.
Oh, so everything is.
You're guessing the key, you're randomizing the data.
So everything is the same except that one value. That is one. There's one. The correct value is one above.
Not necessarily.
No, that just means that the wrong value, there's one wrong value above that one.
I thought the correct value was. I'm confused now.
Okay.
So there's one other guess.
Yeah, it
Doesn't mean
says-
it's 7 or 9. There's just another number that is actually correct, but it's saying
So-
you're quoting it. Like,
Suppose 4C was the correct value for here.
Yeah.
Okay.
You guessed 08.
that might have a correlation of like 80, and 4C
And
has 85.
4C has a correlation of 0.85,
And,
and you got a correlation for 08 of
82.
0.82, right?
You guessed wrong.
So you
But
guessed
you're
wrong.
close.
I mean, I guess wrong. I get that.
It's just if you get like 100, then you're pretty far off.
So, well, maybe I'm gonna understand this one more thing. Say there was a 3S, a third value, which had a correlation of 0.83. Does that make it? If I guess.
Well, that may
That would be like
So-
there's two. Sadly.
Okay, so if you guess 0.8, if you guess this value that was 0.82,
it would
this number would turn into 2 because there would be 2
Oh, I
Two
see.
values are.
values ranked higher. These are not necessarily the correct values.
But it's got the most correlation.
Yeah.
Yes,
Gotcha.
that's a highest correlation on the graph.
Gotcha.
Okay.
This one's a little confusing.
Good slide.
What?
It was a good slide.
So the top shows Tiny AES, bottom shows ABR CryptoLib. Although they look the same, they look different. They're both, you can extract data from both of them. All right, they do look different. So from a simple power analysis, basically view, they look different, right? You see differences in data. But when we look down to the algorithm that we're using, correlation power analysis or differential power analysis, we can find the point using statistical method instead of trying to look by hand. Yes, Tapadar.
So Tiny AES, is that a different version of AES, or is that
Tiny AES is just a library for generating for AES. AER CryptoLib is another one that has AES.
So is it like 128.6?
No, it's the same AES 128 electronic code book mode, but it's two different algorithms. I'm trying to show you that you have two different algorithms that produce the same result, but you get a significantly different waveform. Same processor.
Gotcha.
Yeah, when I was reading about AES online, they said that you could actually hard code the final output with just a single like 1K byte file or a single 4K byte file, depending on how many rounds and which one you were doing.
Right, and it's a pretty small algorithm, which leads me back to that question on the homework, I believe, or it was a quiz or a homework or something. Some people were like, well, passwords on embedded platforms, it's because it's because you can't hash them. Well, you can hash them. There's no problem. There's no problem with actually hashing them. You can store them. It's not a big deal, but a lot of times it won't be hashed. But it doesn't mean it can't be hashed. Right.
What was the question?
The question was something around.
There's one of the questions you gave.
Hashing versus embedded.
The question was. Does anyone remember the question?
I'll look at it right now.
It doesn't matter.
Okay.
Because I didn't get a full score out of
Oh.
it. But
Hashing versus encryption.
Huh.
That was the question.
No, that wasn't
Let me
it.
check this. They can be salted on an embedded system.
Yeah, some people said that they can't be salted or they can't be hashed on an embedded system. That is not true.
They can just take so long.
It takes longer. It may take longer depending on the abilities and
Passwords are not
capabilities.
salted in embedded systems.
Christ.
Thinking in terms of an embedded system, why are embedded systems more vulnerable to password attacks than typical desktop?
Okay, that's a question. So why are embedded systems more vulnerable to password attacks? And some people said, well, the password can't be salted or it can't be hashed. It can be hashed. It can be salted. A lot of times it's not. Okay.
I've said that a lot of times. They don't follow the default password.
Default password is another one. Yeah.
I said because you have to store it on you have to store it on board the chip. If you
Yes.
salt it, it's going to take a lot more overhead.
It's not going to take much more overhead. It really doesn't.
It's just random.
Typically, you can get access easily to most embedded systems because they're dirt cheap and they're all made pretty much the same way.
4 bytes.
For some of them, yes. You have that default password issue that we were talking about. So here is a graph of tiny AES versus AVR cryptobit. We have the number of traces here, and I'm just trying to show you that, you know, even coding them differently and they look differently, you can essentially get the same number of correct keys in the same amount of time, regardless of how it was coded. Right, so the two algorithms that I mentioned here are not actually designed to be resistant to DPA and CPA style attacks anyway. So here's another example of that signal to noise ratio issue we're having.
Signal?
So on the scope, we can reduce the signal to noise ratio. If we keep the, that is basically your horizontal, vertical graticule knob, right? So if we keep the same number of traces as well as the same number of samples per trace, we'll see an increase in the entropy as we increase the volts per division of the vertical scale. In this example, we have 10,000 traces, 10,000 points per trace, asynchronous sampling at 100 megasamples per second. You can reduce the number of traces required, the points per trace, and the sampling rate if we use synchronous sampling. Synchronous sampling allows you to reduce the number of points you take, the number of traces you use, and the sampling rate that you also use. Okay, so that's the advantage of synchronous sampling. And here is basically me showing, well, if I basically vary the vertical scale here, right? Vary the vertical scale as I increase the graticule, right? Each graticule on the scope, each box on the scope. If it represents 2 millivolts versus if it represents 50 millivolts, you basically decrease the success rate as you decrease the signal to noise ratio. Okay? Does everyone follow that?
For 10 millivolts seems to be pretty good.
What?
The 10 millivolt has a higher success rate.
Right, and at a certain point, you just get really loud success rate when you just change that sampling rate to, or not your sampling rate, but your signal to noise ratio. So again, this is a graphical representation of those tables. Right? Increasing the number of traces increases the correlation coefficient, or the signal to noise ratio. So let's see here. As you increase the number of traces here, you got to collect more traces, but you get a much better difference between the incorrect and correct values. Right? And when we move to, let's say, 100 traces, I believe actually the correct, you no longer get the correct value. This was probably the correct value. There's 1, 2, 3, 4, 5-ish, around 5-ish values that rank higher. So that PGE would probably be 5, right? In this case, because this is the correct value, but there's points here that rank higher than that correct value. Okay? So you can see that when we reduce the number of traces, 100 versus 5,000. Okay, so let's say let's say part of the attack, let's say you want to mask, right? You want to mask, and we're going to get into more on this on Monday, but let's say we want to mask the signal. Let's say we're going to put noise in purposefully to block the attacker, right? Let's put in noise to block the attacker. So if we simulate this in Python, we basically take a known good data set, right? And we inject the percent noise, right? As we increase the percentage of noise, we get fewer and fewer correct characters, right? So if we get 0 keys found at around 12% here, or 12% noise injection, does this necessarily mean that all we need to do is inject 12% noise to mask our signal? Does that mean that after injecting some noise into the system, all we have, this is an end, we're protected now. Does that mean that we're protected? Why?
Because they can clean the noise on there.
Right. You can very easily clean up the noise through just either hardware or software filtering. Okay. Any other questions? Comments? So this is using the PSOC 4200, the Cypress device. We have 80,000 data points, 1,000 traces, vertical scale 3.5 millivolts, and we're using basically the start of the algorithm here, the plains X or the key. You see this purple signal here is going high as a trigger to tell us when to basically capture the signal, or where the signal of interest lives. So realistically speaking, we need fewer traces. So the power supply I was using was kind of dirty. Also, I wasn't zooming in properly. And you're going to kind of work through this yourself in this class. For your work later, try the following. Start with the following. 10,000 points per trace, 1,000 traces, asynchronous sampling, obviously because we don't have synchronous sampling equipment available for everyone. Again, this would be a group work. So it's 2 to 3, maybe 4 people working together. Obviously pick someone on the same campus. Okay. So what we want to do when you do this is set the scope to trigger when you get to the sub-byte stage. This is essentially where most of your leakage is. You can probably get away with something else, but the sub-byte stage is the easiest to attack, so we're going to attack that portion. Basically capture something similar to what I've captured here. We're going to set the scope to filter at 20 megahertz on your first channel. So the signal this yellow signal, the channel 1 signal, you set the scope to filter 20 megahertz, right? The bandwidth is set to 20 megahertz because if you do not set that, you're going to get more data points here. You're going to get more data points, but those data points are just noise. So bandwidth limit your scope to 20 megahertz. That's extremely important. Okay?
20 megahertz.
20 megahertz. Yes.
Is the sub-byte stage particularly vulnerable because it's doing a lot of substitution, so it's doing a lot of load and stores?
It's doing that load and store, but it's also because it's nonlinear.
Okay.
Nonlinearity makes it easier for the algorithm to attack. Let's see, the code saves data points, save only the data points where the trigger goes high. So what I'm saying is you can get away with figuring out where this trigger goes high and trigger goes low and capture only those data points, yeah.
Can you remind me what non-linear means again?
So for that sub-byte stage, right? Mm-hmm. That table is designed to be nonlinear.
Okay.
I don't know how to describe that off the top of my head. I guess it means that it's not like a 1-to-1 mapping, right? It's not a 1-to-1 mapping. It's just like, okay, if you have 4C, 4D, 4E, it doesn't go linearly, right? It's kind of like 4C maps to 5A, or I'm just making this up right now. It's not linear.
I kind of get that. I kind of get this.
Okay. So we'll perform the correlation power analysis on the known plain text and original round key to avoid having to reverse through the AES algorithm, which would be required with another ciphertext. Remember, we can attack the front end of the algorithm or the back end. We're going to attack the front end, right, where it starts, because that's kind of easier. Note that, I spelled that wrong, but note that the experiments in this class, we don't use the protected versions of AES. They do have protected libraries out there that are basically would make it way, way, way harder to attack these. But we're just kind of like going through and trying to see, well, is there leakage and can we attack this, right? If we were naive in implementing our system, can we attack it? There's something called DPA contest, differential power analysis contest version 4. There's version 1, 2, 3, 4. For protected implementation, it's basically a contest of security researchers to see who can protect the algorithm, right? What methods can we use to protect the algorithm or attack the algorithm, rather, right? I think this one's more of an attack contest. Things that we could do to improve the lab setup include opto isolator for the UART TXRX. because you will get noise through the UART-TXRX. You could probably put a PCB design together too to improve the signal to noise ratio, because a lot of the system has like wires dangling out which act as antennas. Okay, so microcontrollers on newer processors may use lower voltages, right? As we go forward, we keep dropping this voltage. It looks like 5 volts and 3.3 volts and 1.2 volts, whatever, 0.9, 0.5 volts, right? So it gets harder, particularly on newer devices. Okay, so the brand architecture silicon process does not reduce the chance of a power attack, right? So I did this on an XMega 128. Well, Colin O'Flynn did it on XMega 128. I did it on Cypress PSOC. There's people who have done it on microchip, PIC 18. It doesn't matter what the brand, the architecture of the silicon process. The target can be a microprocessor device with any size data path, right? Data path size does not matter. Or an FPGA or even a soft-core processor, right? It's just the data path size, it may help, but if you think about it, AES algorithm is a byte-oriented algorithm, so it's probably just going to do it 8. It's going to do it 1 byte at a time, still, even on a 32-bit. So it's still going to probably leak the same. Right? So different devices may require a different strategy, and the signal-to-noise ratio will be different. Can anyone tell me why the signal-to-noise ratio on an FPGA would be lower than, let's say, a microprocessor?
It's running everything in parallel, so there's more processes.
Well, that's true. But what else about the FPGA versus the microprocessor?
The FPGA is all faking hardware implementation, so there's actually a lot more gates everything's going through.
Well, the FPGA is not faking hardware implementation. It is actual hardware. It's actual silicon, right? So the FPGA is just reconfigurable hardware, right? It's reconfigurable hardware. So when you have that reconfigurability, what's the problem with the FPGA versus a real microcontroller? Instantiating a soft-core processor on an FPGA versus a microprocessor.
Is it the type of memory that you need to use?
It's not necessarily a type
It's
of
easier
memory,
to
right?
target a specific point on a microprocessor because it's always there.
Well,
Who guys taught you 231?
You didn't.
No, I'm asking Wilson though.
Long. He's like the only person.
Oh, they won't say they're smart.
I'm sorry, you said what?
Never mind. So the point I was trying to make with the FPGA versus a microprocessor is FPGA can be basically reconfigured to be anything. And with that reconfigurability comes a lot of switch matrix, a lot of wiring. That switch matrix and wiring introduces noise, right? If you introduce noise, it makes it harder to target on an FPGA. So you're going to get a lower signal-to-noise ratio on the FPGA. Okay. So again, simple power analysis is trivial to prevent. First-order DPA, CPA attacks are also easy to prevent, which we'll go over on Monday. A substitution step was used as it is the weakest step of the AES algorithm, but more advanced attacks don't necessarily rely on this step. We don't even have to attack AES. We can attack any algorithm we really want to. We just find a weakness and exploit the weakness of the side channel leakage, that is. Attack is not feasible in the field, requires some preliminary setup and understanding, and the synchronous sampling significantly improves convergence of subkeys if you can implement it. You cannot always implement synchronous sampling. Okay, so what I want you to do is take a look at scope_capture_AES_serial.py. That's a Python script that we'll be using for lab, or I don't want to call it lab because it's not a lab. It's basically your assignment. You're just going to happen to be in the lab. So when using the code, you have to change the COM port of the USB to UART converter, as well as your USB address for your particular computer's scope. Tech Visa will tell you that scope address, and you're probably by now you're used to the COM port changing, so you'll just put the right COM port for your USB to UART converter. Also look at the CW_AES guest pi. This is basically the AES code, the correlation power analysis code that will run on all your data. I'm not going to ask you to write these algorithms, they're already written, but we will be using this in our implementation. So please take a look at it when you can. References are done, and before we go, remember to submit your quiz by 3 o'clock today, or you will get a 0. What?
15 minutes.
You have 15 minutes?
Oh man, just enough time.
No, that's
Oh.
how long they have to turn it in.
All right, okay, you have 14 minutes left to turn it in.
Quiz, guys.
So remember to turn in the quiz. Does anyone have any last questions? Because we do still have 4 minutes.
Yeah, so when are we supposed to get together to actually do the in-class not lab?
Extras. Kill the lab.
Oh, I don't have it up.
No, you don't.
I don't have it up. If you look at the course calendar, it'll have basically there's 1 week that we're going to spend on hardware encryption stuff on in lab. I'm going to we won't have the Portland group. I don't know yet, but the group in Klamath Falls will go to 119 to work on it.
Yeah, it's Friday, week 5.
So it's week what?
Week 5 on Friday.
So Friday, week 5, what I'll do is I'll just send it I'll record an example of how to kind of get you set up, right? But for you guys in Wilsonville, just form your groups, let me know who you're working with, and basically work when you want to, emailing me when you need to, okay? You do need to get that scope, and you need to go to Fong and get the hardware. There's going to be that red board, or the reddish board. So you'll need that, you'll need a power supply and the scope. So if you can use that at work or at on the Wilsonville campus, that would be great. You can schedule that at your own time.
Okay, and that's on that's upcoming week 5, right?
Week
Yeah,
5
week 5
Friday should be when you at least you start looking. I don't care if you do it Saturday, Sunday, just start it and get it done get it done before the due date, whenever the due date might be. And I think it's called assignment 7.
10 to 7.
Right. It's either 6 or 7. I believe that's the first kind of hands-on lab that we're going to do. Keep calling it lab, not lab, not lab.
Oh, assignment.
Assignment. Any other questions?
No, I don't think so. I may not be able to sign into class next Wednesday.
It's fine. I don't take attendance.
Okay,
Not anymore.
so, but I will watch the video. So.
Yep. Sounds good. I will see you guys next week. Have a good weekend.
All right.
Yeah, you do the same.
Yeah.
Alright. See you Monday.
Trying to take my units test for me.